Last episode, you added the identity shortcut, the residual connection, and watched the gradient walk 6 layers deep without dying, every bar sitting flat at 4/10 instead of collapsing to 3.2e7. The shortcut kept the signal alive. This episode is about keeping the training alive, batch norm, and almost everything you've been told about why it works is wrong. You've heard it fixes internal covariate shift. Hold that thought. By the end, you'll see what it actually does, and it has very little to do with covariate anything. Start with the textbook story so we can take it apart. Pre-activations stream into a layer with some mean and some variance. Here, mean 4.2, variance 9.1. The claim is the distribution keeps shifting as the layers below it update. The upper layer can never settle, and that internal covariate shift is what slows training. Batch norm, the story goes, freezes the distribution so the layer always sees mean 0 unit variance inputs. Clean story, mostly wrong. Keep the numbers though, 4.2 and 9.1 are real, and we'll track them all the way through. Here's the mechanic that is real. Batch norm subtracts the batch mean and divides by the batch standard deviation. X balls exit 420, 9.10. Square root of 9.1 is about 3.02. So every activation gets recentered to mean 0 and rescaled to variance 1. That part is genuinely true. After this step, the batch is standardized, full stop. The misconception isn't that it normalizes, it's what that normalization buys you. Now the part everyone forgets. If batch norm stopped at mean 0 unit variance, it would be a straitjacket. A tand or sigmoid unit fed only the linear middle of its range can never use its saturating ends. You'd have crippled every nonlinearity in the network. So BN immediately undoes its own normalization with two learnable knobs: gamma scales, beta shifts. Y .gx plus y, set gamma to 1.4 and beta to 3/10, and your mean 0 unit variance signal becomes mean 3/10, variance 1.96. The network is allowed to put the shift back, even allowed to learn the identity and cancel BN entirely. So BN forces 0 mean is just false, it forces 0 mean, and then hands the network the steering wheel. Variance 1.96. Where did that come from? This is the rule people fumble. Scaling a variable by gamma scales its variance by gamma squared, not gamma. 1.4 squared is 1.96. Beta, the shift, moves the mean to exactly beta, 3/10, and touches the variance not at all, because adding a constant slides the whole distribution without stretching it. So output mean equals beta, output variance equals gamma squared. Mean 3/10, variance 1.96. That's the whole transform, and it's the table you'll compute in the file. So if it's not covariate shift, why does batch norm work? Here's the real answer, the one from the 2018 How Does Batch Normalization Help Optimization paper. BN makes the loss landscape smoother, more Lipschitz. A Lipschitz constant is just the steepest the loss is allowed to change per step. A big constant means cliffs and ravines, where one step overshoots. A small constant means gentle slopes, where every gradient step is trustworthy. Without BN, this network's landscape has a Lipschitz constant of 8.4. With BN 2.1, same network, same data, the terrain got 4 times gentler. Sit with why that matters more than the distribution story. A smoother landscape means the gradient you measure here still points roughly the right way one step over there. So you can take bigger, more confident steps without diverging. That's why BN lets you crank the learning rate. It was never about the activations being pretty and centered. It's that BN reshapes the bowl you're rolling down into something with no surprise cliffs. 8.4 down to 2.1. That one ratio is the entire reason the layer earns its place. One last myth to bury. Batch norm and the bias term do the same job, so drop one. Half right for a sneaky reason. Beta is a learnable shift, so a separate bias right before Bn is genuinely redundant. Bn subtracts the mean and erases it anyway. So you drop the bias, not Bn. People remember they're redundant and reach for the wrong scissors. Keep Bn, kill the bias it makes pointless. OpenNN batchnorm.py. It's one forward pass through a batchnorm layer by hand, no framework magic. And then a tiny landscape probe that measures how steep the loss is allowed to get before and after Bn. 4 blocks: feed the pre-activations, normalize, apply the learnable scale and shift, then estimate the Lipskits constant both ways and print the table. First block, the pre-activations. We fabricate a batch whose mean is exactly 4.2 and variance exactly 9.1, the numbers from scene 1. We assert them so the rest of the file can't drift. If the batch ever stops being mean 4.2, the script dies right here instead of lying in the figure. Second block, normalize, subtract the mean, divide by the square root of variance plus a tiny epsilon, 195. The same floor we've used for every normalization in this course. There, only to stop a divide by 0 when a unit is dead flat. Outcomes x, mean 0, variance 1. We assert that too because it's the one claim the textbook actually gets right and we want the figure to honor it exactly. Third block, the learnable knobs, gamma 1.4, beta 3/10, by oral j, x plus y. Then we read back the outputs moments. Mean lands on beta 3/10 and variance lands on gamma squared 1.96. The code computes them rather than hard coding. So the table on screen is genuinely the array's own statistics, not a caption we typed. Fourth block, the landscape probe. We sweep a small step along the gradient direction and measure the largest jump in the loss. That ratio is the effective Lipschitz constant. Run it on the raw layer, 8.4. Wrap the same layer in Bn and run again, 2.1. The function returns both. We print the ratio, and that single line, Lipschitz 8.4 to 2.1, is the headline the figure draws. So batch norm normalizes activations on the way to its real job, which is sanding the loss landscape from a Lipschitz of 8.4 down to 2.1. Nearly 4 times smoother, 4 times safer to take a big step, not covariate shift geometry. Next episode, we stop dissecting single layers and put the whole thing together. We train a real small network end to end and watch every piece you've learned cooperate. The loss falls, the gradient norm drops, and we land on 94%.